computer, and then let's put this. Okay, so hello everyone. As always, thanks a lot for joining us another day, another class. Today is day 7, and we will have two main topics today. We will start with basically complementing what we did in the last class. So if you remember, we studied how to provide a different type of coupling, and we work on the J1K coupling. But then I mentioned that I realized when preparing the class that one of the transitions also has a JJ coupling. So I said we will start this class just seeing how to add this JJ coupling and checking the difference that we can find in the results. And then after that, we will move to learning how to create an atmosphere in RH format. Okay, so the process, as you will see, is relatively simple. But as you will also see, I will ask you to really pay a lot of attention on units and also on the convention for different things, like how, so where the atmosphere starts and finish, or how you define a positive velocity, or what is the meaning of positive velocity and negative velocities. So those things we will check in detail, because usually each code has a different convention, and this is usually the causes of misunderstanding and messing things. So I will also try to show you how I usually check that things are okay, and is essentially synthesizing profiles and checking that things are reasonable. So if you add in a velocity that you believe will introduce a Doppler shift that is towards the blue, then you synthesize the profile and you check that this is happening. Or if you you make a mistake with the units, then you may see that the amplitude of the polarization signal is too large, or that the intensity is flat because you have a temperature that is like 100,000 Kelvin or something like that. So I will just show you how I usually do it. It's always good to have some recipe. But the important thing is that as each code has a different way of doing things, please be aware that it's important at the beginning to double check that you are doing everything in the proper format. Okay, and then just as a very quick thing, we also discussed that we saw that there are some acronyms, or I mean instructions in the keyword.input that they start with RLK something. And you asked me what does it mean, and I said I didn't know, but we will check with Han. And I already checked with him, and he said that is basically the initials of Robert's name. So Robert Al L Kurux. We don't know what is the L, but basically it's the 3 initials of his name. And it means that you are introducing an extraction that is related with files related with Kurux. It could be the Kurux line list or other things. Okay, so then it's just that. Okay, so let's start with the first example that I mentioned. So in this case, we are in the RH distribution, RHF1D, and then is Kurux config 3. And there we will have that I have loaded these files, and this is scene.pro, that is the ideal procedure that we will check, and then the RH specific instruction files. Okay, so then let's go ahead with the beginning. As I said, it's just complementing last week's class. So we are just going to start from the last part of the class, and then we will add the JJ coupling. So as a summary, I copy things from the last class, the atlas. So you will see the plot of the atlas. Then remember that in 2 classes, in the previous 2 classes ago, we created a Taylor wave file. So I just copy here the instructions and then how you save it. So this is the same. And then here we are going to run case 7 from last class. That is the case where we improve the log.gf values of the Kurux file. And we simplify the file with only a specific lines, and we improve the log.gf values. But in this case, everything is treated under LS. So it means that we use the Taylor wave file, the Kurux 3, so this is the normal one without any changes in the coupling. Then we added a magnetic field because we wanted to check the difference between the polarization profiles when adding different couplings. And then this is extraction on the keyword input. Okay, so if we run it, remember we just read the wavelength vector, the intensity profile, we normalize to a given wavelength that is the same between the other profiles and also for the atlas. And then we read the Four-Stokes parameters and we normalize them to that continuum intensity and we save the file. Okay, so just as a summary, we are running the third file. Then we are just using the magnetic field here and then in the field-free approximation. So if we run this, let me check that we are okay. So we run this and it just works and then it finishes in 171. Okay, so then what we are just doing is bringing back the example where we just copy from Kurux all the information, and it means that two transitions that they should be treated with a different coupling, they are treated in this run under LS approximation. Okay, so we just let me comment this for avoiding making mistakes. And then these two. Okay, this one. So then the next step was to upgrade the Kurux file, adding these the different coupling schemes for the transitions that needed. So I copied these from the Kurux function in the RH distribution. And remember that it was very simple. In the case of the LS coupling, we just needed to put inside brackets the spin and the angular momentum. So this is 2s plus 1. And then we check how to do it in the case of JK coupling. So we needed to transform it in this way. I keep the same explanation here, but we are not going to cover it. And then we said that there was a third possibility, that was the JJ coupling. And now this is what we are going to check. Okay, so just I will bring this back. Yeah, so here. So if you remember the silicon 18550, let me go to day 7. So here we will have a screenshot, and this is from Valdi. So if you see in the upper level configuration, it says that it's a JJ configuration, and there's some information about the level configuration. Okay, so this is inside today's folder, so you will be able to check it. And I copy that information in this case. Okay, so this is what Valdi database said, and also the same in the NIST database. So we need to transform this to this instruction. That is the one that RH requires. So then the first thing is just be aware that we are now using this type of symbol. For the LS coupling, we use these brackets, but now we use this one. And also the next thing is to just get the J1 and the J2 values. Okay, this is usually provided as this expression, but you will see that is also here and here. Okay, so then J1 is just 1.5 and J2 is 0.5. And we provide them as numbers. Okay, so then it will be simply this 1.5 and then this 0.5. Okay, so then the next step is to provide the angular momentum, so L1 and L2. And this goes in the traditional spectroscopic notation based on Roman alphabet characters. Okay, so then in this case it's 2p, so it's a p, is L equal 1. And then in this case it's an S, so it's L equal 0, and we just copy the S. Okay, so then transforming this instruction for this level will be 1.5, J equal 1, J1, sorry, P, that is the angular momentum of that level, that is L equal 1, then 0.5, that it comes from here, you can see it here, the J2, and then S. Okay, and it's basically
one question. It should be a small letter or capital letter, or is the same?
I think a small letter works, but I don't know if it's the same. Han, do you remember?
No, I don't remember.
I have it like this.
I think internally the code may transform it into uppercase, but
Yes.
I will check while you give the lecture. I will check,
Yes.
and we can come back to this at the end.
Okay. Okay. So in this case, it's working. I think working like this. So I mean the code is running. So I think it could be a small letter, but it's a good question. I think,
yeah, because in the case of JK, there was a difference between
Yes.
small and capital
Yes.
letters. And then,
Yes.
okay.
In this case, yes. Yeah.
Yeah.
Yes, there it has to be a lowercase.
Yeah. Yeah. Okay. So then we have it. So then we just go to the file that we modified. If you remember, I just duplicated the lines, and what I kept commented was the original Kurux file, and the new one with the new format. You can see it in the other lines. So you remember that we added the JK coupling here, the others are LS, and now we are adding this JJ coupling here. Okay. So then for that, if you remember, we need to, yes, before running the code, there is a bug in the code that I found this week. So when I was checking this, and if you go to the kurux.c, Fortran, where is, 1 second. So let me go back to, so in the main distribution, you go to Kurux, sorry, this one. And if you go to 107, so in your current version here, there's a 5. So it says JJ count 5, but you need to update it to 4. Okay, so I put it here that now you have this and you need to change it to 4. I think Han will update it in the GitHub, but if you want
it is already updated in the GitHub right after I fixed it for you. Yeah.
Okay, so then just upload with the new version, or if you just are running, just change it like I did by hand, and then just type make in the inside RHF1D. Okay, and we'll upload the routine. Okay, so then now let's try to run the code. And if you remember, we need to add a few changes. So the first one, we need to change the name of the file that we are using. So now it's 4. Okay, and we put a comment. Let me just remove this file here. But then remember that for this context, we also added the instruction RLK explicit in the keyword.input. In my case, I added it just behind this one. So then I just know that it's related to Kurux. And so just we can comment this line, and then we just run. And again, after running the code, I just load the wavelength, the intensity, and the stocks profiles, and then I save them in this file that I'm not saving in the class just to avoid messing up things. And then today we are going to compare the case with Kurux line list, always assuming LS coupling, and the case this one, where we add JJ or JK depending on the level. Okay, so then just let's run it. Okay, and then it finishes in this line. Okay, so if we go back to the folder, we will see this plot. Okay, so just let me make it a bit bigger. So 7 is everything is LS coupling, and 8 or blue, it's including these new coupling schemes. So if you remember from last class, we noticed that this line was slightly different in intensity, and we also saw the impact on the polarization profiles. This is because the polarization profiles, they depend on the Stokes height, but also because we are changing the lambda factor, because we are including a different coupling. And what we are seeing now is that this line, that is the one that we added the JJ coupling, it seems that basically doesn't change. I really compute the difference, and there's a small difference, but basically in this context, we don't see difference. So yeah, so it means that in this case, probably there's a large difference between LS and JK. And in this case, probably the difference between the two is not so important. Okay.
So Carlos, I checked, and it can be either lowercase or uppercase. It is always transformed to uppercase. So,
okay, perfect.
so in the case of JJ.
Thank you. So then this one is correct, right?
Yes, that is correct, but it could also be uppercase in both cases, or mixed, or
okay, good, thank you. So then the conclusion is that, so in the case of the transition that was related, so it had a upper level a JK coupling, we saw a big difference. In the case of the JJ coupling, it didn't change, so I would say that this is interesting. Maybe with a different transition, we will see a difference. But for me, the important thing is the only difference, or the only thing that you need to do is change labels in the Kurux file to really include the correct coupling. So even if you don't see difference or some spectral lines, don't hesitate on including the proper coupling, because it's just changing a label. So it's always good to aim for the best option. Okay. So this was a bit fast because it's from previous class, but do you have any question before I go ahead to the atmosphere part, or was more or less clear this part? Okay. Okay, I will assume that. Basilio, do you have a question?
No, it's okay.
Okay.
It's okay.
Okay. So then I will assume that was more or less clear, but also you saw that I have the instructions and everything in the script, in the idle script. So you can always check and reproduce the example. Okay, so now we go to another folder inside Arrange, and I call it Atmos Create. And here we are going to load several things. So we will load again the keyword.input, and we will load just this one to double check that we are using the correct one. And the same with Kurux.input. Sorry, I need to load all the things, and I didn't want to have it just to avoid confusing with the previous one. I will load this one, and I think I have no, I need this one. Oh, sorry, this is a favorite. Fancy this one, sorry. Okay, so then let's see what we are going to do. Okay, so day 7. Well, as always, I just in case I remove everything and I feel more confident. So we can start. And the idea is, if you want to provide an atmosphere to Arrange, you need to provide 2 files. Okay, so the first file that has this, so a name.atmos, it will contain what I defined thermal. I don't know if this is the correct name. And then the magnetic component is provided in a different file that in fact is optional, although I would say that is very interesting to have it. And it's a name and .b. Okay, so then let's start with the thermal pass. That is one that is mandatory. And let's see first what is everything, so what each item means, and then we will learn how to modify it and then create a new one. Okay, so the first part is the header. So let me cover these items, and then we will go to the atmosphere falsi.atmos just to check it. So I will go step by step. So the first one is that you can have a header of any extension, and you need to add asterisk at the beginning. And I think this asterisk is probably heritage from multi right hand.
Yes.
Yes, because usually we comment with the other symbol. I forgot the name. This one.
Correct. Yes.
The
part. Yes.
Yes. Okay. So then just
the heritage from multi is the reason that the B file is separate and in ASCII format. Well, for the multi-dimensional cases, it is binary, and so it's a bit. It looks a bit random, but
yes. Yeah, it's fine. I think it works perfectly. So it's okay. Okay, so then you have the name of the atmosphere. This is usually used later when RH is reading and assigning IDs to different structures. Then you have the type of height scale. So you could have either geometrical height, you could have a column mass, or you can have optical depth at 500 nanometers. Okay, then you also have the number of depth points and the gravity value. And this is just one number. And then we start with height dependent atmospheric parameters. And we have initially five columns. So first is the height scale, then temperature, electron density, line of sight velocity, and microturbulence velocity. Okay, so let's stop here, just check an atmosphere and we will see what we are saying. So first part, you can have any comment here. Then, as I said, you have the name that you want to assign the atmosphere. Then the type of height scale you use. In this case, it means geometrical height. Then you have gravity. In this case is log of the gravity. Then the number of depth points on your atmosphere. And then the 5 columns that I mentioned. So it's height, temperature, electron density. In this case, a macro, or could be, you can call it line of sight velocity. Both are okay. And this is the micro velocity, okay? Microturbulence velocity. And then after that, you have another 6 columns, and they are also height dependent. I will show you, and then we will see what it means. You can have here, at the end of the first part, you have another 6 columns. And these are hydrogen level populations, and I think it's level 1, 2, 3, 4, 5, a number of protons. And I think, if I'm correct, Han, the code assumes a 6-level hydrogen atom, including the first 5 levels, or quantum numbers from 1 to 5, and ionized state, right?
Yes.
Okay. Okay. And then the idea is that hydrogen populations are optional, but only if you provide as a height scale the mass column or column mass. If you provide geometrical height or optical depth, it's a requirement on the file. Otherwise, the code will crash, and then I will tell you that I need the hydrogen populations. Okay, and there's another option that I don't usually use, but I think it exists, that is providing only one value, and that is the total hydrogen population instead of the 6 columns. And as I don't use it, I think we may try it in a different class, and I will check it with Han if I configure it properly. So in general, the standard case is this one. So having 6 columns, and then you have here 1, 2, 3, 4, 5, and then protons. Okay, and it's the same as before. So you have, in this case, depth is 70. So then you will have 70 values of each case. Okay. So then let's start with notes and advices and warning. So the atmospheric parameters are, they appear from top to bottom. Okay, so then the first,
hello?
Yes.
I have a question.
Yeah,
so
go on.
I wanted to ask, so height and tau long optical depth is understandable, but what is the meaning of column mass? I mean, what does it physically signify?
Okay, Han, do you want to help me with that?
Masses.
So what is the meaning of mass column?
It's the integrated density from the top. So it is well, it's a standard thing that is used in radiative transfer, but it is the density in this case in CDS integrated from the top. So it's the total column mass to a certain height.
Yeah,
Okay.
this is gram per square centimeter. Then you are integrating density over height, and then you are labeling each depth by the integrate of the mass column from the top to this position. And you are saying that you are in a certain level because the mass column from the upper top of the atmosphere to this level is the integration of density by distance is this value. And you are labeling different layers.
It goes very similar to the optical depth in many cases.
Okay.
Optical depth is also an integrated quantity, right?
Yeah.
Right.
Yeah.
Okay.
In fact, if you are in hydrostatic equilibrium, the mass column is the derivative of the gas pressure with height. It's exactly because
yes.
then you can also use pressure as a label of for heights, but in this case, Carlson wanted to use mass column. There is a lot of people that works in. I think that infrared people in galaxies and nebula works with mass column as a depth distance.
Mm-hmm. Okay, thank you. Okay,
Thank
so yeah, okay, so then let's continue. So then what I was saying, so please be aware that the first point of this vector is the top of the atmosphere. So we do the opposite on SER and this side, so just be aware of that. Then the second note is that RH works internally in SI units, but as you see in this file, these ones are in, I think, CES. Yeah, so then just be aware that what you see there is not what internally RH is reading, and we will see later what is the impact of that. So just be aware of units, okay? So then in this case, you will see geometrical height is kilometers, temperature is Kelvin, and electron density is centimeters. Velocities are in kilometers per second. And I think gravity, I'm not sure. Yes, I will put it here because now I'm thinking. And the population density is also in centimeters, so in CES. Okay, and also the final comment in this case is that the velocity convention is, I think, the opposite of the spectroscopic one. So what I mean is that positive velocity means material moving up. That is a bluer motion. And this is the opposite convention that we have, for example, in SER and design. So just be aware of that when you are providing a velocity or when you are just playing with a velocity, that you are considering what a positive and negative means in RH context. Okay. Okay. So then let's start step by step, and let's read an atmosphere. In this case, we have the FALC model. So we can read it using the ideal routine read 1D atmos. And then if we do it, let me see, I think I can run it. Second. Okay. Yeah, so we have this here. So basically what is printing here is what I copied here. So then it's reading the ID, that is the name that we are assigning the atmosphere. Is giving us the gravitation. In this case, it's not in log scale, it's a normal scale. I think it's meters per second, hand probably.
Centimeters per,
centimeters per second. Okay, okay, yeah. Okay. And then you have the depth, and then the scale, and then you have the vector. So this is the geometrical height in this case, temperature, electron density, line of sight velocity, microturbulence, and then these are the population. So you can see that is depth times 6. Okay. So then here again, I will repeat it a lot during the class, units. And what I mean is that the units provided by read 1D atmos are SI units. So these are RH units. If you go to the program, let me see if I can go here. There's a part, so it defines the transformation from CES to SI. And at some point here, it says convert to RH units, and you see that is done before saving the files. So then it means that the output of read 1D, it's in SI. So temperature is Kelvin, electron density is meters, and then velocity is in meters per second, and then also density will be meters, cube meters. Okay, so just be aware of that. Okay. Let's make a plot of the atmosphere that we have read. So I think there's a stop here. Just let me remove this one. So then we will run until this point. Oh, sorry. Yep. Yeah. Sorry. Just let me comment this. I forgot this one. Okay. Okay, so then it stopped in line 146. That is this one. Okay, so we go to this folder and we open this file. Okay, So I'm just plotting here just to give you an example of the atmosphere. This is geometrical height, this is temperature, and this is electron density, ionospheric velocity, that is 0. And then the microturbulence that is usually has this pattern in some of the FAL models. Okay, so if you see, I'm plotting the velocity in kilometers per second. So, and this one says meters. So what I'm doing in the plot is dividing by 1000, because as I said, these are SI units because are RH units. So these are meters per second and meters per second. So I just divide by 1000 and I get kilometers. And in this case, I don't do anything and I just get meters, cubic meters. And just what I'm doing is this structure that we read here. So this atmosphere is what I'm just adding height versus temperature and height versus electron density, height versus velocity and microturbulence. Okay. So then now that we know how to read and now we have atmospheric parameters in RH format, let's do something very, very, very simple. That is just modify one parameter and then rerun the synthesis. So, but before that, sorry, I ran the synthesis of this example with this atmosphere. So we just run and now let's check that we have everything. I'm just copying everything from last class. So then we have that in the curux.input, just 1 second. In the curux.input, we are reading the index 4, the 4 version. That is the one, just 1 second, okay. That is the one that included the JK coupling in the level of the silicon 8536 and the JJ coupling in the 8550, okay. So so this is correct. We now we check that we have the magnetic field, we have this, and then this. Okay, so let's go to the keyword.input. Now, sorry, I added this one because before we never changed the atmosphere, but now we are going to do it later. So now this one is an entrance that we are going to change. So let's be sure that we are using the original atmosphere. Then we are using the tailored wave file. Now we are also making the explicit the new version of the curux file. So we are including all the coupling schemes. We have the magnetic field example 1, and we have field free approximation. Okay. So then we run the test, and as before, we just read the output and save the stocks profiles. Okay. Let me see if yeah, this stock is commented. So now it will end in 200, hopefully. Okay. So now we run the synthesis of the original file, atmosphere plus a magnetic field from the previous class. And now is when we are going to modify the atmosphere. Just let me comment this to avoid mixing and messing things up. And what we are going to do is something very, very simple. We are just going to add some velocity and with a gradient. Okay. So then what I do is first compute, just to have it in case later we will need it, the number of points. So just with this instruction IVL, you get the number of points of, for example, velocity. Then I create just a linear file that is increasing with height, and it's this one. And I put it in kilometers per second because I usually, it's easy for me to think in kilometers. And then, sorry, this is kilometers. Yes. Yes. So then, as this one is just an increasing velocity, ionospheric velocity, but as remember, the first point of the vector is the top of the atmosphere. So I want to have the opposite behavior. So I just flip the velocity and then I just put it in meters per second. So just let's make the plot and then we will see what I did. Okay, so then the next run will stop here, hopefully. Okay, so then what I added is figure file C, this, this one. No, this one. Okay, so before there was a constant velocity, and then I added a velocity that is in a line of sight velocity that is increasing with height. I added just a linear one, and the idea is that the geometrical height is not uniform. So if we go back just 1 second to file C, you will see that, for example, here the change is every 2 kilometers more or less in a few steps, but then in lower layers it changes like 50 kilometers sometimes. So the height scale is not uniform. So when I created a uniform velocity and the geometrical height is not uniform, it looks a bit weird like this one, but it's just an example and it will work fine. The important thing is that we have a velocity that is above 0 in all the cases. So this is 0, and this is 2 kilometers and goes up to 10. And around 1000 kilometers that we can set that calcium line is sensitive more or less around this region in the line core waveform. It's around 5 or 6 kilometers per second. Okay. So then let's compute the profile with that atmosphere. So then what we need to do now is, yes, we need to write down that new atmosphere in RH format. So what we're going to do is to use the routine called write 1D atmos. And the only thing is that there was an error on line 14. So this part that I have here highlighted was not there. So I just modified and I included in this folder. So please copy it in your folder, and probably Han will update also the GitHub version. It's just this that was missing. And I noticed because I was using height scale in this example. Okay, so then after correcting that, what we need to do is to define the things that we saw before that are needed for an RH atmosphere. So we first give a name, and then we are going to create a structure that contains all the items that we had in the ATM, the atmosphere structure that we read with read1D atmos. So we define the ID as a name that is defined here. Then we provide a gravitation value that in this case is centimeters per second. And then we provide the number of test points that we computed a few lines before. Then the type of height scale that we use. And then as we are just changing the velocity, this case is simple because we are just providing the same height as before, the same temperature as before. So this ATM.T, the same electron density. And now the only thing we change is velocity. So instead of having here ATM.V, what we have is vel, that is the velocity that we created just here. Okay. And then we just finish with, again, the same microturbulence and the same hydrogen population value. So we just added a new velocity, and the rest of the things are the same. And then we just call array, so write 1D atmos. We give the name of the structure containing all the information and a file name. In this case is fancy mode. Okay. So we run it and we create a new atmosphere. And now let's compute the profile with this new atmosphere to check what is the impact of adding a velocity in the Stokes profile. Okay, so we are going to run, and as always, double check. And in this case, for example, the only thing that we are changing is this one. Okay, so we go to the keyword.input and we change the ID or the name of the atmosphere that we are providing. In this case, is fancy mod. Okay. And then again, we read the output and we save it in this file. So let's see if this runs. Okay. And we finish here. Okay. So now just let's compare it. So I restored case 1 and case 2. 1 is without velocity and case 2 is the same atmosphere but with a velocity. Okay. So let's go to the folder and we compare this one. Let's see. Yes. Okay. So let me make it a bit bigger. So black is the previous computation, and then blue is the one with when we added a positive velocity. So we see a shift that is good because it means that we added the velocity and the line is shifting. And we also see interesting things like in this case, for example, in these lines, you can see that the amplitude of these two is basically the same, but the amplitude of these two is different. And this is because if you remember, I added a gradient. So it's not a constant velocity, it's a gradient along the line of sight. So we are introducing asymmetries in the Stokes profiles. It could be the amplitude, the Stokes V, it could be the area. And also we see the asymmetries in, for example, in Stokes Q or in Stokes U. Okay, so then the velocity is there. And it's the results are reasonable. And also we see that the profile is moving to the left. So it's moving, it's a blue shift. So if you remember, we said that our H convention is positive velocities, is material moving up. And then this will introduce a blue shift in the profile. Okay. So then what I'm going to say again is just please double check that. So as always, double check everything. And what I mean is that you know the sign of the velocity, so you know what I said, that it has to be a blue shift. So if you see that it's different, then you could have a wrong sign, or maybe during the program you change it and you didn't know that you were changing it. So always when you run just once, be sure that you are using the proper velocity convention. And then again, units. So if you remember, we were playing with units and I said, be aware that maybe centimeters or kilometers or meters. So we saw that the profile was slightly shifted. So then the idea is you may compute more or less how large should be that shift. It could be either just having the velocity around 1000 kilometers, how that should be translated into wavelength. So this is homework for you. Or the opposite, you can compute how far the calcium line was shifted in wavelength units, and then transform that to velocity and check if this is around 5-10 kilometers or if this is 200 kilometers. So if this is 200 kilometers, then you made a mistake in the units or something. Okay, so those are very simple things, but at least when you are trying one or two cases, double check that, and then you can run, for example, for a simulation or things. Okay. And then one thing that we have not tried yet, and I think probably not soon, is that there's a keyword in the keyword.input that is called hydrogen LTE true. We have always commented that line, and it's because we are providing hydrogen populations that were computed in non-LTE. So in this case, we didn't change the atmosphere, so we keep this. But sometimes you may have a simulation, for example, and you don't have hydrogen populations. So one way of using geometrical height is to compute by ourselves the hydrogen populations. And this usually you can do it in LTE. So if that is the case, then the atmosphere that you provide needs to be labeled with this one. So you need to activate this one. But in this case, and in the next class, that we will have also hydrogen populations non-LTE in the bifront atmosphere, this will be always commented. But just in case, be aware of that. If you play with hydrogen populations, also update this keyword accordingly. Okay. And I think that's all regarding the thermal part. And now let's play with the magnetic field. Okay. So the B file. So we need to provide the three components of the magnetic field in spherical coordinates. So it means the modulus and then the inclination and the azimuth. Okay. So you have an example in the manual in section 4.51 that I basically copy here, adding different values. So you defined as I said, the strength of the magnetic field. We need to put the same number of points that we have in the thermal part. And then in this case, let's add 1,500 gauss. Then you need to provide also the inclination. also for having a value different than the one we are using, I just put it 145. And then the azimuth, I just picked 15. Okay, I usually think on Gauss and degrees, but as you know, the RH works on SI units. So you need to transform the field strength to Tesla. And then also you need to transform to radians, the angles, okay, the inclination and the azimuth. So if you do that, then you are ready. And then we just follow the instructions to create in the XDR file, similarly to what we did for the wave file. And it's just open the unit, then put this instruction, give a name, and then just put the parameters one after the other, and just you're ready to go. Okay. So after that, the only thing remaining is to run again RH. And now what we are going to do is to maintain or to keep constant the velocity. So we are not changing the velocity from the previous example. So we have a gradient along the line of sight, but we are changing the magnetic field. Okay, so then we will run RH. We will keep the modified atmosphere. And now what we are going to change is this one, that instead of example 1.b, now will be example 2.b. Okay, so we go to the keyword.input, we go a bit down, and here. So we comment this line, and now we are providing a magnetic field. Is still constant with height, but it has a different polarity, okay, and a different field strength. And as always, we run. Let me check if I commented the previous. So I will comment this one, and this one to avoid mixing things. So we will run the computation. We will read the output, and in this case, we will save it as a case 3b. Okay, and after that, we are going to repeat the previous plot and adding this new case. Okay, so just let's see if this runs until 9,529. Okay, so now we have this new atmosphere. Okay, so we have black, blue, and red. If you remember, the difference between black and blue was velocity. So you can see here that it's essentially the same, but we have some asymmetries. And now we have the red one that, for example, in this case, it's very clear that there's a big difference because we had 45 degrees in the case of blue, and now we have 145. So we are changing the polarity. So these are the wings, and then these are the two lobes, and they have opposite polarity. We see that also the amplitude of Q and U is different because we are having different angles. And we see that in principle, there's no big difference in Stokes I, because previously we had 1000 Gauss, and now we are using 1500 Gauss. That for these lines is not so big difference, I mean, for the calcium line. So, but in principle, it's working, and you can see that it's consistent. So we change the polarity, and the Stokes B profile they have different polarity, and we change the angle, and they have different amplitude, Stokes Q and U. Okay, so let's see what I had here. Yes, this is what I said. So then we are already in the summary part. So let me do the summary, and then I will ask you for questions. So then, in general, we need two components to provide RH with an atmosphere. The first is the thermal part. So it contains the scale, the temperature, the velocities, and also the hydrogen populations. As I said, just be aware about units because we have some, let's see, it could be tricky because the legacy from multi, so when you print a file, the Atmos file, you see CGS, and RH works in SI units that I think is accepted in most of the physics areas except astrophysics that we go our way with CGS. So it's not really RH fault, I think it's the opposite. but just be aware that different codes we could work on CES and NSI, so just be careful about that. And then my advice is double check things, and there are ways of doing it. So if you have a given velocity, you can check if the profile is moving red or towards the blue, and then from that estimate if your assumption is correct. And the same with the profile. So if your amplitude, so if your intensity is flat, the profile, then probably your temperature is too high. Or if your profiles are 100% amplitude, it means that you probably have a very big magnetic field. And I think just that. Yes, and the same with the magnetic field. So it means that we are ready, I think, for performing synthesis with much more complex atmospheres. And next week we will do that. We will learn how to take a snapshot from the Bifrost code and put it in a reg format and then run the synthesis with this same configuration in terms of lines, wave files, Kuruks, line lists, and everything. We will do the computation for a more complex atmospheres. Okay, so then before going back to the presentation, is there any question that you could have from the last part?
Just one comment. Yeah, okay. Just one comment. Before I said nonsense,
Yes.
the mass column in the case of hydrostatic equilibrium is exactly the gas pressure divided by gravity. Gas pressure over gravity is the mass column. Okay.
Okay.
Yeah, I said the derivative from something.
You said geometrical height. I took note of that, so I will I will check it later.
It's gas pressure over gravity.
Okay.
Divided by gravity. This is the mass column.
Okay.
Okay.
Okay. Okay. That's all. Hi.
Hello.
Hello.
So I have two questions, Carlos.
Yeah.
If I remember correctly, the microturbulence velocity cannot be included in spherical arrange. Is this the case, still the case, or there is any change on that?
The microscopic, yes, they can be included, but not the macroscopic. So not the line of sight velocity. There is no.
Yes, macroscopic. Yes, sorry. Yeah. Okay.
Yes, no, that is not included, and neither are magnetic fields.
Oh, neither magnetic fields.
Yeah, no, because just the way the spherical transfer is solved with the different impact out, the projections become complicated, and I haven't taken the time to work that out.
Okay. And another question I have is that, so is it possible to include the non-homogeneous field, non-homogeneous magnetic field file as an input? Non-constant magnetic field as a function of height.
So you mean a magnetic field with a gradient?
Yes.
Like the velocity.
Yes.
Yes. So I added a constant one for simplicity. But next week we will check some of the profiles from the Bifrost snapshot, and everything is changing with height. That's nothing constant.
Oh, okay.
So it's just that, for example, you can try at home as a homework. So in this case, instead of adding this sentence that is a constant magnetic field with a height, just include a gradient and run this example, and you will see that it works. Okay. But in principle, we will see. Yeah, we will see next week that azimuth, inclination, and everything is changing a lot, very, very quickly with height, and in principle, it works. Okay.
Thank you.
Yeah, thank you. Okay, so any other question before I move to the presentation?
Hi, I just wanted to ask, so the stick code, which is based on RH, has the opposite convention of line of sight velocity, I think. Like there we consider negative as upflow and positive as downflow.
So you mean design code or stick code?
Stick.
Yeah. This is probably, so in design we also have the same convention, and this is probably because it's more focused towards fitting spectra, and then they may be more comfortable working on this. In our case, it was heritage from CER, so it's fine. But the truth is that it's just convention. So having one or the other should be okay. I think depending who you ask, one convention is more reasonable than the other. So, but I think we are used to one in case of, for example, SER, and now in my case with RH, I'm also used to the other one. So yeah. But in case of this, I will mention it. It's a SER convention that is the opposite from the one we're using here. Okay.
Yeah, I think if you work in forward modeling, you are more tied to models, to simulations.
Yes.
And there it makes more sense to have upward velocity
yes.
as positive. While if you do like SIR, you do inversions, you're more tied to the spectroscopy where it's often the opposite. So.
Yes.
Yeah.
Okay.
Thank you.
Yeah. Thank you. So
can I point one thing out?
Yes.
Carlos, there are now for those of you who prefer Python, there are Python routines that that are included in the GitHub, in the RH GitHub. If you haven't looked since maybe a month or so, or 2 months. And especially the manipulation of atmospheres, I think is more straightforward in the Python routine than it is in the IDL, because I think I've taken a little bit more care in how to treat units, and so so there it's easy to really read in an atmosphere, modify it, and write it back as a different atmosphere. So for those, I think there's a Python notebook that is included in the distribution that shows you how to read, modify, and write input atmospheres.
Yeah, I think I was here, right? So I haven't checked it, but I think is this Python, right?
Yes.
And this RH analyze. So this is what you're saying.
Yes.
Right?
So those are the routines. I don't know.
Yeah, maybe I didn't update it because it's from May.
It has significantly been updated.
Okay. So yeah,
and I think there are some notebooks that are included now there as well.
Okay. Yeah. So then the things you have learned from IDL, you now applied on Python. so now it's better.
I think it is more straightforward there, but you still have to be aware of the units.
Yes. Yeah, I think the main advice from this class is really be careful about units and find ways of being certain that you are using the proper units. That is basically playing with the synthetic profile and check that it works.
And one of the things that, and I'm sure you will address next week when we talk about BFOS, is that in multi-parlance, and also that's what I took for all the other versions as well, is that the top is the first index. So that's kind of sometimes confusing, and people transferring data, transferring a simulation into RH format will make the mistake of having the order wrong in the Z direction.
Yes. I think the next week class, probably 80% of the time will be transforming the atmosphere.
And I can't tell you how big of a headache that was to program the upside down projections and things like that.
Okay, interesting. Okay. So then let me go back to the presentation. So yes, let me see. Okay, so 1 second. I think, we were here. Okay, so homework, very simple. This is the same as the 2 previous classes, so just pick a transition or a spectral region where you are interested in working, and try to pick up the lines from the Kulux file, and then create a file like we did. And be sure that the levels that you are including, they are under LS coupling, or if not, then modify them following the instruction from last and today's class. Then try to create an atmosphere. So for example, in the case of Dato, as I was recommending him, instead of a constant magnetic field, just add a gradient, and then save and run the example and check that it looks reasonable. And then Yes, so this is what I said, experiment with values. And the idea is that some of you may be comfortable or used to work with photospheric lines, and now adding chromospheric lines, it's a bit different. So for example, I would recommend you to try to experiment with things like this question. So if you add a magnetic field like 1000 Gauss, 2000 Gauss, do you see the splitting, the Siemens splitting on the calcium line? Do you see the three components or not? And if the answer is not, so can you try like 10,000 Gauss, and will this make appear the magnetic field? So play with those things, because the lines are different and they behave a bit different. So getting some intuition of just by playing with the atmosphere, it's very helpful in the future, mainly when you are inverting the profiles. Okay, and then next class, as we said, it's going to be adapting. This is the main word, a bifront atmosphere to RH format, and then running and checking that it's reasonable. I will just prepare the script to run over a given field of view. I will run it at home, but then I will give you the results, and then you will try to do it. But the idea is that after that, in the future, when we start learning the parallel version of the code, we will do the same in parallel. So it will be just transforming the atmosphere in the same way that we will learn next week, but then we will prepare it as an input for the parallel wrap, and then we will run it in parallel in a cluster or on a server, and it will be really, really fast. Okay, so then the next class again next week, next Friday. Is there any question before I wish you a nice weekend, or any comment? No? Okay, so then enjoy the weekend, and I hope to see you next week. Okay, thanks a lot.
Bye-bye. Thank you. Bye-bye.
Bye.
Bye bye.
Bye. Thank you.
Bye.
Thanks. Bye.
Nice to see you.
Thank you.
Okay, let me stop sharing.